Hey everyone, and welcome back to The Explainer. Today, we are diving into something we literally do every single second, yet rarely think about. We're dissecting the hidden mechanics of motion. Like, how does a stationary object actually manage to get moving? It turns out the physics bridging a completely still object to one hurtling through space is governed by some incredibly beautiful, and frankly, kinda counterintuitive rules. So let's unpack exactly how movement is generated.
Let's kick things off with a bit of a brain teaser. What exactly enables a massive, incredibly heavy rocket to move upward against the crushing pull of gravity? I mean, we all know the engine pushes it up, right? But think about it for a second. When it's way up high in the atmosphere, or even out in the absolute vacuum of space, what is that engine actually pushing against? There's no ground up there. It really opens up this fascinating gap in how we intuitively understand propulsion.
Just look at the fire and smoke fiercely pushing out of the bottom of that rocket. Why is all that downward thrust the absolute 100% crucial ingredient for upward flight? To truly wrap our heads around this massive feat of engineering, we actually need to scale things way down. We need to look at something much, much smaller.
Section 1. The mystery of movement.
Okay, so let's walk through this awesome little tabletop experiment from our source material. Imagine a toy car with a fan mounted right on top of it. Step 1, you turn the fan on and boom, the car moves forward. The blown air simply pushes it along. Makes perfect sense, right? But here is step 2. You take a piece of cardboard and place it right behind the fan directly in the path of the air. Step 3, we observe. What do you think happens? Does the car still move forward?
Let's look closer at this setup. You've got a battery powering a dyno, which spins a propeller blade. Pretty standard stuff. But notice the back of the car. There's this blue pillar holding a removable piece of cardboard. When that propeller starts spinning, it blows air directly backwards straight into the cardboard that's attached to the exact same car.
Well, when we actually run this experiment, the car just sits there. It completely stops moving. It literally becomes a self-defeating fan car. So what's going on? Why does the car stop moving when the cardboard is added? The fan is still spinning just as fast. What invisible rule of physics is holding this thing in place? To solve this puzzle, we're going to need to gather a few theoretical tools.
Which brings us to Section 2, Newton's third law. This right here is the golden rule of interaction. Whenever one object applies a force on another object, the second object simultaneously applies an equal force in the opposite direction. It really highlights this absolutely beautiful symmetry of forces in our universe. You see, forces never ever exist in isolation. They are always, without exception, a mutual exchange.
Let's break this down into really simple terms. The first half of this exchange is called the action, and that's exactly what it sounds like. It's simply the force exerted by one body onto another, like your hand pushing a table or a little fan pushing the air. That right there is the action.
And then we have the inseparable second half of the equation, the reaction. This is the force experienced by the body that is actually doing the acting. And here's the kicker. This reaction force is always equal in magnitude and opposite in direction to the action force. It's a 2-for-1 deal. They are a definitive package deal.
Section 3. Action and reaction pairs.
So let's picture two identical trolleys connected by a compressed spring-loaded piston. A little hammer is about to tap the trigger. When it does, bam! The spring releases, pushing the trolleys apart. Now, because these forces are an equal and opposite pair, the trolleys push away from each other with equal opposite velocity. The action of pushing the left trolley creates a simultaneous reaction of pushing the right trolley. They move together but apart, if that makes sense.
The really crucial point here is understanding these specific rules of these pairs. First off, they act simultaneously, right at the exact same time. Second, they involve exactly two objects, no more, no less. Third, and please pay close attention to this one, they do not balance or cancel each other out to make zero net force. And why is that? Well, it's because of the fourth point, they act on different objects. If I push a solid wall, the action is on the wall, but the reaction is on my hand. They don't magically cancel out because they aren't happening to the same object.
Moving on to Section 4, Defining the system.
Now in physics, we always have to define exactly what we're looking at. A system is basically just a collection of objects being considered together, often within a specific boundary. Think of it like drawing an imaginary box around the things you want to study. For our toy car puzzle, the system is the car, the battery, the fan, and the cardboard attached to it. All of those pieces live inside that one imaginary boundary.
Okay, so once you define your system,
your forces fall into two main categories. An external force originates from outside your system boundary, and this is what actually causes acceleration. An internal force, on the other hand, originates from within the system itself. And here is the absolutely crucial takeaway. Internal forces do not affect the overall motion of the system. I want you to take just a second and see if you can connect this logic back to our self-defeating toy car puzzle.
Got it? Well, here is the solution. When the fan blows the air backward, that is a force, right? But because that piece of cardboard is physically attached to the car itself, the blown air just hits it. The action and the reaction are happening entirely inside the car's system boundary. The fan pushes the air pushes the cardboard. Because this mutual exchange of forces originates from within the system, it is an internal force, and therefore the car cannot accelerate. To make the car actually move, the air needs to be pushed completely outside the system, acting as an external force against the surrounding environment. It's like trying to pick yourself up by your own shoelaces. It just doesn't work.
Section 5. Real-world jet propulsion.
Before we scale all the way back up to giant spacecraft, we can actually observe this exact same physics model scaled down on a tabletop. I'm talking about balloon jet propulsion. It operates on the precise mechanics we've just been talking about. Just picture inflating a balloon, maybe taping a straw to it for stability, and then letting it go. The action is the balloon powerfully squeezing and pushing the air out of the back. And since we know forces always come in pairs, what is the reaction? Well, the air applies an equal and opposite force pushing the balloon forward. It accelerates. And because the air escapes the balloon system entirely, it acts as that all-important external force needed for movement.
Which brings us right back to our opening hook. If you connect that balloon directly to a massive NASA rocket, the principle is completely identical. The rocket doesn't need to push against the ground, and it definitely doesn't need air outside to push against. The action is the rocket's engine violently forcing fire, smoke, and gas downward out of the nozzle. The equal and opposite reaction is that exact same exhaust gas pushing the massive rocket upward into the dead vacuum of space. Action down, reaction up. It's that simple and that incredible.
Honestly, once you see this symmetry, you kind of can't unsee it. It governs absolutely everything moving around us. Which leads me to a really thought-provoking final question for you, based on everyday life. Next time you simply take a step forward, ask yourself, are you pushing the Earth, or is the Earth pushing you?
Think about it. If the ground were perfectly smooth, frictionless ice, you couldn't move forward at all. Why? Because to walk, your foot must exert an action force backward against the ground. And in response, the Earth exerts an equal reaction force, pushing your body forward. You are quite literally being propelled by the Earth reacting to your step. It's this beautiful mutual exchange of forces, happening with every single stride you take. Thank you so much for joining me on this explainer. Keep questioning the world around you, and I will catch you in the next one.